work is nothing but force times displacement, and that can be written as integral F external dot dr, which is equal to F electric dot dr, where VA is the potential at A and VB is the potential at B, and W is the work done, and Q is nothing but the test charge. Any charge comes near another charge, it will experience a force as soon as it is under the influence of its electric field. So in order to calculate the potential energy, I only have to calculate the work done in keeping that charge in that particular point. Hey all, I am Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence. And today we are going to start a new chapter, which is electrostatic potential and capacitance. So in the first chapter, we were discussing about electrostatic charges, their nature, behavior, electric fields, and their other properties. And now we are going to study about electrostatic potential, potential energy, capacitance, resistance, and all those things. So what exactly is electrostatic potential and what exactly is electrostatic potential energy? They are very similar but slightly different in nature. Electrostatic potential is actually defined as the potential between 2 points, defined as the work required to be done by an external force in moving a charge Q from one point to another point in the electric field of any arbitrary charge configuration, that is plus or minus Q, without any acceleration. And electrostatic potential energy is defined as the amount of work done by external force in bringing charge Q, again without acceleration, from infinity to a particular point. So what does these two mean and how exactly they are connected, how they are similar, everything we'll be discussing in a short bit. But I just wanted you to know that this is the actual definition of that particular words, and this can be particularly challenging to understand what exactly energy is and what exactly potential is and how we can wrap our thoughts around that particular concept. And this is the actual definition of electrostatic potential and electrostatic potential energy. Electrostatic means nothing is in motion, static means it is in rest, and these are the definitions. So this is actually the written definition or the mathematical term which explains what the definition actually was. This equation explains to us that WP, that is work from R to P, is given by the integral of R to P F external dot dr, and F dot dr is nothing but work done. So we already know that work is nothing but work is equal to force times displacement. In physics, work does not mean that you get up early and go to a job and earn money. In physics, work means that there should be a force applied and there should be a displacement produced. And force can be denoted by the letter F and displacement can be denoted by the letter R, dr, or x, dx. That is dx being the small amount of displacement produced and r also being displacement. You can either use r or x depending upon your choice, and dx or dr being the small amount of displacement produced. So anyways, we can say that W, that is the work from a certain point to another point, R to P, is given by integral R to P F external force dot dr, or F dot dr, nothing but work, which is equal to F electric dot dr. Now, what exactly does these equations mean will be discussed shortly. Have patience. This will be clearly explained in just 2 minutes. I just want you to see what exactly we are dealing with, how the equations are, and then I'll give you a clear-cut instruction on how we got these equations and how we arrived at these conclusions. So, work done by external force in moving a charge Q from R to P is given by this particular equation. For now, keep this equation in your mind and know that work is nothing but force times displacement, and that can be written as integral F external dot dr, which is equal to F electric dot dr. Why there is a minus sign, what is this electric force, and everything will be explained shortly. And this work done against electrostatic repulsive forces gets stored as potential energy. And what this is will also be explained in 1 second. And coming to electrostatic potential difference, it is just the difference between point A and point B. Let's say that point A has a particular potential and point B has a particular potential. Then we can actually say that the potential difference between those 2 points is given by the higher value minus lower value. That is, if point A has a potential of 5 volts and point B has a potential of 2 volts, then we can say that VA minus VB is the potential difference, which is given as 5 minus 2, which is nothing but 3 volts. So that will be the potential difference. To find the potential difference, you just need to minus or subtract the higher value minus the lower value, and you will get the potential difference at a particular point. And this can also be explained as electrostatic potential difference between 2 points in an electric field is the work done in moving a unit positive charge from one point to another point. And unit positive charge just means that it is a test charge. Unit meaning 1 and positive charge just means it's a positive, that is a plus sign charge which has a magnitude of 1. And that can be written as potential difference, that is del V is equal to VA minus VB, or by the definition it is the work done per unit charge. So W indicating work done per unit charge. So where VA is the potential at A and VB is the potential at B and W is the work done and Q is nothing but the test charge. And now let us get to what exactly is electrostatic potential and potential energy due to a point charge. So what exactly is a point charge? Point charge is nothing but, let's say we have a charge Q in an empty space. So we already know that we don't need any particular energy to keep that particular charge in space. So we can keep this, let's say this is a positive charge, we can keep this in an empty space, and we already saw that when we place a positive charge like this in space, there will be electric field all around it. And we know that if it is a positive charge, then the field lines will be directed outwards in all directions like this. And we don't need to have any stress, tension, or we don't have any problem keeping this in space. But imagine that I am bringing a positive charge Q from a long distance away to this particular charge. Why am I bringing it? That happens in nature. That can happen sometimes when there is a charge present in a system and then another charge slowly approaches it. So imagine that for ease of convenience, let's say that there is a big positive charge Q here situated in space, and me, that is HK, is bringing a small charge Q. I have put it in my pocket and I'm walking towards this particular charge. And as I get closer and closer, we have already seen in the first chapter, positive and positive charges wants to repel away from each other. So they want to repel away from each other. So I have to exert a force as I get closer and closer to this positive charge. Or as soon as I enter into the vicinity of this positive charge, I will start to experience a force. We already have seen that also in the first chapter, given by the equation F is equal to QE, or E is equal to F by Q. We have already seen that. So we know that that force experienced is nothing but the electric field, which means that when a unit positive charge or any charge comes near another charge, it will experience a force as soon as it is under the influence of its electric field. So imagine that I'm bringing this charge from infinity. So this is a really far away point which is infinite distances away, and I'm walking there with a charge in my pocket and I'm walking closer and closer to this particular charge Q. And let's say this distance is R and I have this test charge at the point P. So we know that these two are positive charges. So in order to keep those charges there, I have to put in energy. I have to do work. That is because imagine that these two charges are brought closer to each other. So since they are positive charges, they innately have a tendency to go away from each other. So in order to keep them together, I have to put more energy into it. I have to do work to keep it close to each other. If we can imagine that they are connected together like in the form of a string, there will be tension. They want to go away from each other, but they are connected through a string. That string holds all the energy. There is a spring in between my hands. If I put a lot of energy into that, put a lot of work in squeezing that spring, that energy is stored as potential energy. So potential energy is nothing but the energy due to its configuration or position. So in this particular instance, all that energy, just like squeezing in a spring, if the charges are negative and positive, if it's attractive, it will be like squeezing in or keeping it apart. Now the charges are positive and positive, which means that they are repulsive in nature. So it is like using a spring or using a string. A string will be a much more neater example. So let's say I'm using a rubber band or a string, then this rubber band or elastic string will be keeping these two charges from flowing apart from each other. So they are kept like this. If I get a scissor and cut it, they will go apart. So in order to keep them together, I have to put in work. I have to put in energy. And this energy in keeping those particles at that particular point is known as potential energy. Or we can simply say that in keeping this charge, even if it is negative, positive, or whatever it is, in order to keep this charge in the vicinity of another charge, I have to put in energy. So the total sum of all the energies due to its position, due to its interaction with the electric field around it, due to its vibration, everything accounts for the potential energy. So we can simply imagine that since these two are repulsive in nature, in order to keep them together close by each other, I have to put in energy because innately they want to move away from each other, but like a string attached to it, they cannot move away from each other because I am putting in energy. Because remember, this charge is in my pocket as I walk closer and closer each other. Let's say this is the particular point Q, which has immense amount of positive charge, and I have a test charge Q in my pocket. As I approach closer and closer, it becomes harder and harder for me to get closer to this particular charge because it is repelling me with immense force. So in order to stay there, I have to apply equal amount of force. In order to get closer to the positive charge, I have to apply even more force. So in order to stay in this particular position, let's say at position P, I have to apply equal amount of force. So we already know that there will be a force experienced for this particular charge, and that force is in the direction of the electric field. And since this is a positive charge, electric field will be radiating outwards, which means that the direction of force will also be in this direction, and this is also a positive charge, which means that the direction of force will be along this way. So we can say that the electric field will apply an electric force in this particular direction, and that can be indicated as FEL. And this will be equal to the external force, or simply I can say that I don't want to take external force. This will be equal to the force I apply to keep that particular charge in that particular point in space. That is, again, imagine there is a positive charge. In order to stay here, I have to apply equal amount of force to balance the repulsive forces offered by this particular point charge. In order to get closer, I have to overcome that force and provide more force or do more work. But to stay here, I have to do equal amount of work that the repulsive forces, or in this case, the electric force is doing. So I can say that the external force I apply is equal to the electric force but opposite in direction, which means that the electric force is trying to push it away, but I am doing, the external force is trying to keep it there or try to move forward. So the forces are opposite in direction. The negative sign indicates that the forces are in opposite direction but equal in magnitude. Okay, So in this particular instance, I can say that this is the force applied by HK. So I'm coming from there with a positive charge in my pocket. As I'm approaching closer to the big charge Q, the big charge will repel me with a force which is the electric force, and that will be in that direction. And I have to do, that is HK have to do work in order to stay at that particular position, and that will be in the opposite direction. So that is the primary assumption we have to make. So as I told you, I'm coming from infinity to a particular point, let's say P, and I have a test charge in my pocket. So let's say like infinity is too far of a stretch. It just means that I'm coming from a really long distance. Let's say that distance is denoted by the letter small r. So I'm coming from infinity, and that distance is denoted by small r. And this particular distance, that is from origin to this particular point P, is denoted by capital R. Anyways, so we only have to worry about what is the work done by me in bringing this unit positive charge from a really long distance. For now, let's take it as infinity. So infinite distances away, I'm carrying a unit test charge in my pocket and I'm walking closer and closer. As I get closer, I have to do more and more work, which means that the electric field is getting stronger. This particular charge is trying to push me away, but I am doing exactly equal amount of force and I'm slowly inching my way forwards. Why slowly? It is very important that I don't run or try to do anything drastic, because I am doing it slowly. Because if I apply acceleration, that is, if my velocity changes, then the whole equation becomes unstable and it becomes really hard for us to find out what exactly was I doing. So in order for that, I am making slow movements. It is very slow. So I'm like moving this much slower at constant pace, ensuring that there is no acceleration. So I am coming from a really long distance with a unit positive charge in my pocket and approaching with steady step with slow increments. So which means that I am being repelled by the electrostatic force in that direction. So which means that I have to apply a force. This is the force applied by HK, which is in this direction. So it is equal in magnitude but opposite in direction, and I have to make small improvements. So which means that I am moving or taking small steps. And in order to keep this particular charge in the vicinity of the electric field, I have to do work, and that work is stored as potential energy. So in order to calculate the potential energy, I only have to calculate the work done in keeping that charge in that particular point. So for that, we will calculate the work done. Work done is equal to force times displacement. Here I am moving at a distance of r. So I'll be moving at a small distance dr. This can be written as f dot dr. Know that this is a vector quantity, force is a vector quantity, and work is denoted as f dot ds or f ds cos theta. This you have studied in your previous classes, which just indicate that work done is equal to force times displacement, and cos theta is nothing but the angle between force and the displacement produced. So where am I traveling from? I'm traveling from infinity to that particular point. So I can say that integral infinity to a point r I am traveling. So FHK, that is the force I am applying, dot dr will give the work that I am doing, that is WHK, which means that the work I am doing is equal to the integral, which means that I am making small steps of dr, small steps. If I integrate all that small step, if I add all that small steps, I'll get the big R. So we know that the equation is f dot dr. So I can say that FHK dot dr will give me the work I did, and which in turn will give me the potential energy used in this scenario. But I don't know how much force I'm using. I don't know actually. I'm just going against a particular force that is pushing me. I'm just using equal amount of force that the force is trying to push me with. So I can write this as equal to the force that is opposing me. And what force is that? That is the electric force, and that is the electric force, and we can write it as FEL dot dr. And from where to where? It is not from infinity to that particular point or infinity to r where the point P is, but the force that the electric field is applying is directly in the opposite direction. So we can say that it is from r to infinity. The only thing is that it will be in opposite direction, so we can put a negative sign. Okay, so we know that if we calculate this or this, it will be equal in magnitude, which means that in order to find out the work done, or in turn we are finding out the potential energy, which is indicated by the letter U. So in order to find out the potential energy, the only thing we have to do is find the work done by electric field. So in order to find out the potential energy, I only have to do or find out what is the work done by the electric force in this particular situation. So we already know that work done is nothing but the potential energy, and the potential energy will be given by the work done by me in order to bring the unit positive charge from an infinite distance away to a particular point in space, and that can be calculated by finding the force applied by the electric field in order to keep me away. So that will be in the opposite direction, and we have to solve this, and we don't have to worry about what is F dot dr, which is equal to F dr cos theta, because here cos theta or simply theta is equal to 0 degrees, because the electric field also in the same direction as the electric force applied, which means that this and this E are both in the same direction or parallel to each other, and the angle between them is simply 0 degrees, which means that cos theta is also 0, which means that cos theta is also equal to 1. That is, cos 0 is nothing but 1. So we can say that it is simply F dr, as this quantity will become unity, that is 1. Since we got that out of the way, the causes and sines and everything is out of the way, now we have to integrate this equation. So what exactly is, we have found that in the previous chapter, which is nothing but F is equal to, that is K Q1 Q2 divided by R square, where K is equal to 1 by 4 pi epsilon naught. So we will apply that particular equation here, and here Q1 is nothing but the big Q and Q2 is nothing but the small q. So I can again write this as integral r to infinity 1 by 4 pi epsilon naught q divided by r square. So 1 by 4 pi epsilon naught r square and capital Q and small q. Since both of them are positive, they are repelling in nature, and we have to put a dr in the equation because dr is there, and integrate this from r to infinity. So if you look at here, the only possible quantity that can be integrated is the distance, that is dr. So everything else inside the brackets or inside the integral will come outside. So we can write this as q divided by 4 pi epsilon naught integral, put the minus sign here, r to infinity, and the remaining quantity 1 by r square dr. So when we integrate r to infinity 1 by r square, what do we get? So 1 by r square, we can write it as r raised to minus 2. And on integrating r raised to minus 2, we can write it as r raised to minus 2 plus 1 divided by minus 2 plus 1, which means that this is equal to r raised to minus 1 by minus 1 from the limit r to infinity. You can do the integration and find out what the answer is, but you can do it easier by this method. So r raised to minus 2 plus 1 is r raised to minus 1, and minus 2 plus 1 is simply minus 1. So we can write this as minus 1 by r from r to infinity. So we can write this as minus q divided by 4 pi epsilon naught, and simply minus 1 by r, the upper value which is infinity and the lower value which is capital R, and solving this we will get our potential energy. Solving this is very easy. Upper value minus lower value. 1 by infinity, which is 0, minus 1 by R, and the minuses will cancel each other out, and we can say that, and the final result will be q by 4 pi epsilon naught capital R. And if you get a negative sign, don't worry about it. That is because the electric force is in the opposite direction. But in actuality, this electric field is equal to the magnitude of the force we are applying. So we can simply write this as FEL is equal to FHK, which is the force I apply. So we can neglect this negative sign because they are equal in magnitude but opposite in direction. So we can simply write U is equal to, or the potential energy is equal to, QQ divided by 4 pi epsilon naught R. And this is the energy or the potential energy required to keep this particular point charge in space near to another point charge. And this is the way we find the potential energy of a point charge. And remember, this is a scalar quantity. And one more thing, what if instead of coming in a straight line like this, I took a crooked path? That is, I travel like this in order to reach here. Will that affect the equation? Absolutely not, because this is a conservative force like you have seen in 10th and 11th standard. So, since this is a conservative force, it is path independent. So, any path I take, it doesn't matter. The potential energy will be the same. The equation will be same. Now we have seen what exactly potential energy is, and that is given by the equation. And the definition of potential energy is nothing but the work done in order to keep this point charge in space there. That is, the energy stored between these two particles. The energy stored is known as potential energy. It is due to the field interactions, the electrical forces applying on it, and all other forces combined, and that can be called as the potential energy of this particular system. And now we have to focus on what exactly is the potential. So remember, potential and potential energy are different entities which have similarities. Potential is indicated by the letter V. So what exactly is the definition of a potential? So recall the definition I have showed you earlier, and we can say that the potential is nothing but the work done in bringing a unit positive charge from infinity to a particular point. Or we can simply write this as work done in bringing a unit positive charge from infinity to that particular point. And we already have found out what is the work done in bringing a charge from infinity to a particular point, and that is given by the equation QQ divided by 4 pi epsilon naught R, since this distance is R. If you have taken that as small r, then it is completely fine. Now, coming to the potential, it is W by Q, and W is here, and you have to divide it by Q, that is QQ. For this 4 pi epsilon 0, I'm just taking it as K because we already know that, and divided by R, this Q will come here, Q, and these Q will cancel each other out, and then you will have the equation for potential, which is given by KQ divided by R, that is Q by 4 pi epsilon naught R, and this will give you the potential, and this is the potential energy. So potential is nothing but the work done in bringing a unit positive charge from infinity to a particular point in space. We can say that it is the work done per unit charge from infinity to a particular point in space. and that is given by the equation V is equal to Q by 4 pi epsilon naught R. And potential energy is given by the equation Q, that is Q1, Q2 divided by 4 pi epsilon naught R. And the unit for the potential energy is nothing but joules. We already know that the unit of energy is joules, and that is to pay homage to a really great scientist. And just like this, we can say that the SI unit of potential is joules per coulomb by that logic, but nobody says joules per coulomb. We just say that it is volts indicated by the letter. Again, paying homage to another scientist named Volta. So all these SI units are named after them to respect their works. So we can just say that the unit of potential energy is joules, the unit of potential is volt. And now coming to the main topic, that is electric potential due to a point charge, which is the same thing we just derived. That is, we have a positive charge Q, massive charge, and we are bringing another charge from infinity to that particular point, and we will get this equation that we just derived. So it is basically the same thing. So one more thing to keep in mind is that the sign can actually change depending on if it is positive and positive charge, that is if it is positive and positive, or negative and negative, the sign will be positive, if indicating that the forces are repulsive in nature. So if it is positive and negative, then there is attraction in between them, which means that the direction is opposite to each other, which can be indicated using a negative sign. So we can say that potential is a scalar quantity, and that can be negative, positive, or zero. What does that mean? It means that if these two are positive charges, that is like charges, so positive, positive, or negative, negative, then the sign will be positive. If the potential of a particle that is positive in nature, then we can say that the potential can be positive, and then the potential is negative, then we can say that the particle was negative in nature. So for this particular charge, we can say it has a positive potential. This was a negative charge, we can say that it has a negative potential. And if the potential is zero, it just means that it is really far away from the positive charge. How can we prove that? It is very simple. When we are really far away from that point, R tends to infinity. So when R tends to infinity, this becomes infinity, and 1 over infinity is nothing but 0. So we can say that the potential will become 0 if the distance tends to be really far away from it. So that is all about potential energy, electrostatic potential, and I hope you have understood the concept. I'll be back with more potential secrets. So I'll be back with more physics next time, and thank you.